Sandy, could we start or should we wait for other participants?
I usually waited a couple of minutes. Some people connect. Yeah, just in case someone connects, but after that you can start whenever you want. You can you have the ability to share if you want to share something. So yeah.
I will try to share. Okay, I think that you see my screen.
Yes, we can see the screen.
Okay, I think that we can start our first meeting. It is a great pleasure for me that I can meet with you. My name is Paweł Lula. I work for Kraków University of Economics in Poland. And here at my university, I work for the Department of Computational Systems. My research interests are related to data analysis, to artificial intelligence, mainly are focused on the area of analysis of textual documents. But today, during this course, I'm going to talk with you about some mathematical concepts. Some mathematical concepts which, in my opinion, are very important and very helpful when we are thinking about data analysis, about artificial intelligence. I know that our time here is limited, and I thought about topics which are the most important for us. And finally, I decided to talk about three elements. First, about linear algebra. Next, about differential calculus, which is very necessary for optimization problems. And the last topic, which I'm going to discuss, is about probability. I selected these three topics because I think that these areas of mathematics are very close to problems which we discussed within data analysis, within artificial intelligence. So I thought about some algorithms, some methods which are very popular in data analysis, and I tried to identify mathematical concepts which are the most important for them. And in this way, I decided to talk about these three areas. So today I'm going to start with linear algebra. This topic I'm going to continue on Wednesday. And also on Wednesday, I think that we will move to the next topic, which will be related to these parts, these topics from mathematics, which are very important in optimization. Optimization, which is used for learning algorithm very often. And we know that a lot of algorithms have probabilistic character. So also it is necessary for us to know some simple concepts which are related to this area of mathematics. Linear algebra. I'm going to talk about two main types of objects which are discussed on the area of linear algebra, about vectors and about matrices. Of course, during my presentation, I'm going to focus on some practical issues which are related to these concepts. So sometimes my presentation will be far from mathematical discipline, from mathematical rigor, because rather I will try to present some intuitions, some interpretations which are related to these concepts which I'm going to present to you. So we are talking about vectors and about matrices. All these materials which I will use during my presentation, I shared with the help of Sandy with you, so you can find this notebook, and I think that it is possible also to run all these programs which I prepared for you. Because my idea was to use Python as a tool which I will use for presenting some mathematical concepts. Because I think that it is not necessary to perform some calculations manually. We can use Python for performing these calculations. And I think that the knowledge about the way in which we should interpret the results and concepts which we use is the most important. So first about vectors. Vectors are very popular in mathematics and also in computer science. It is a column, or it can be a row with values, with n values. Here we see the example. It is a vector column vector with n elements. This n value defines the dimension of this vector. And we know that if we are thinking about practical aspects, we can create vectors in Python language. We notice at the beginning of this notebook that I attached some libraries and also NumPy library, which is very important and which is our main tool for performing all analysis. So using this library, I can create a vector in Python in this way, using array method. As a parameter, I should put values which I want to have inside this vector. And these values are here defined as a list. So I created a vector with two elements, 4 and 3. And I printed it, and the result is here. So it is a representation of this vector, very common representation. So it is a sequence of numbers. We see on this picture that these numbers are located on defined positions. The first element is on the first position, the second on the second position. So these numbers, indices, they define positions on which we have these vectors, these elements. But of course, we know that in Python language, we have different situation. Elements are numbered from 0 So the first element of this vector is on the position to which 0 index is assigned. So it is a vector, and this vector can be represented in this form in Python. But also very useful is to know how we can present vectors graphically. And here you see very short program in which I tried to present this vector with two values, 4 and 3, on this graph. So we know how to interpret this graph. We have a coordinate system. The origin, the starting point of the system is here in the point 0, 0. And we have a vector which starts at this point, 0, 0 points, and ends in the point for which coordinates are here as values in this vector, 4 and 3. 4, it is a x coordinate, 3, it is a y coordinate. So we see that also it is possible to present vectors in this way. Sometimes vectors are used for presenting some objects. And very often when we use vectors to present objects, we can present them graphically only as points. So we can put a point, we can draw a point in this here in this location for 3, and also it may be a graphical presentation of this vector. So we see that vectors can be presented in many different types. So we know the concept of a vector. We know that it is an object. And with this object, on this object, we can perform some operations. There are two basic operations which we can perform using vectors. The first operation, it is a multiplication by a scalar, by a number. So we want to multiply this vector by one value, one number. So for example, we have this vector which is defined here. It is a vector with elements 2 and 4. And I wanted to multiply this vector by a scalar value by this value 3, which is here. And the results we see here. To obtain these results, we can very easily obtain these results. We need to multiply this value 3 by every element in this vector. We have two elements, 2 and 4, so 2 multiplied by 3 is 6, 4 multiplied by 3 is 12. So it is the result. And here we see this operation, the graphical interpretation of this operation. Our original vector was this vector, 2, 4. This vector is here. It starts in the point 0, 0 and ends here in the point 2, 4. It was presented using this red line. We can see a part of this red head of this arrow here. And we multiplied it by a number. And in this way, this blue vector was created. And we see some very interesting features of this operation. This vector, which was produced using this operation, lies on the same line. So its position is very similar. We can say that it is the same as our original vector. It is located on the same line. It is longer, of course. And when we can compare lengths of these two vectors, this original and this which was produced by this operation. This new vector is longer 3 times. 3 times because we multiplied by 3. So here we saw a very simple example, but it works also for vectors which can be presented in 3 or higher dimensional space. We will talk about this concept, vector space. So it is the first operation, multiplication by a number. Also, for vectors, we can define another operation. We can define a method which we can use when we want to add 2 vectors. For example, we have 2 vectors. The first, A, with elements 4 and 2, and the second, B, with elements 2 and 6. And I wanted to add them. Adding 2 vectors, when I want to add 2 vectors, I must to add corresponding coordinates, corresponding values which we have inside this vector. So it is possible only if the number of elements in the first and in the second vector is the same. Here in this example, we have only 2 elements in the first vector and in the second vector. Of course, we can increase a number of elements. We can, for example, have 5 or 10 elements, but these vectors must have the same number of elements. It is a condition which must be fulfilled if we want to add 2 vectors. So we should remember that this operation, addition, can be performed if we have vectors of the same size. And we should add corresponding elements. So here, 4 plus 2, it is 6, and 2 plus 6, it is 8. So the result is here. Addition of vectors have very interesting also graphical interpretation. These 2 vectors, A and B, we see here. This program I use for generating this graph. I know it is a very simple graph, but it is only for presenting this idea. So we have these 2 vectors. A vector, it is this red vector. B vector we have here. And I added these 2 vectors, and I obtain a vector which is presented here as this blue one. So it is here. How we can generate this vector using graphical approach? When we have these 2 vectors, which we want to add, we can draw a line, this black line which we have here, which is parallel to this vector. And from this point, I'm going to draw a line which is parallel to this vector. And in this point, it is an intersection point for these 2 lines. We have the end of this vector. So if we want to calculate, or maybe not calculate, to create this vector graphically, we can use this method to draw these parallel lines, and this intersection point will define the result of this operation. So we know now these 2 basic operations which can be performed on vectors. Here I showed you how to perform these operations for 2-dimensional vectors, but in the same way we can calculate results of these operations for vectors with more elements. When we are talking about vectors, very often we need to know the length of this vector. It is a length of this line from origin of a coordinate system to this point in which this vector ends. So we can assume that 0, 0 point is here, and this vector ends here, and we want to calculate the length of this line. The idea is very simple. We can use Pythagoras theorem for calculating this, the length of this vector. Here we see a formula, but in Python, it is not necessary to define any expressions because we have in line arg package a function norm, which we can use for calculating the length of a vector. So here, for example, I have a vector with two elements, 3 and 4, and the length of this vector is here, so it is 5. Next operation, when is very often useful in machine learning, it is a calculation of scalar or dot product for two vectors. It is an operation in which we use two vectors. In this example, which you see on this picture, we have two vectors, and in every vector we have 3 elements. And we want to calculate a scalar product. Product, it means that it is related to multiplication operation. But scalar means that the result of this operation will have a scalar character. It will be a single value, a single number, a single numerical value. How this value, scalar or dot product, is performed? When we have two vectors, we should multiply corresponding elements. So we should multiply 2 and 8, 7 and 2, and 1 and 8. And after it, we should add these results. So the result is here, 38. So we see that this operation produces one number as a result. We use two vectors, but the result, it is a one numerical value, a scalar value. So in Python, we can, of course, perform this operation, and there are two possibilities. We can use this function, which is called dot, because first, of course, I defined these two vectors. In these vectors, I have values which are the same as we have here. And I can put these two vectors as parameters, and this scalar product will be assigned to this C object. It is the first way in which we can perform this operation. And here we have the second possibility. This add operator we can use. It means, in this case, scalar product, that I want to calculate a scalar product of two vectors, A and B. And in this case, the result was assigned to D. And these values, C and D, I displayed here. So we see the result, of course, is the same, because here I showed you two different forms, two different notations, forms of representing this operation. We can write the command using these two expressions, these two forms of expressions, but the result, of course, and interpretation is the same. Of course, we should remember about one very important element, that we can perform this calculation only if lengths of our vectors is the same. In this case, it is true, because in the first and in the second vector we have 3 elements. So it was possible to calculate scalar product of these two vectors. Also, we can present a graphical interpretation of this operation. We can see here, I found on the internet this picture. It is very, very nice picture, and in my opinion, it allows us to interpret this operation. This operation about which we are talking now, so scalar product. We have two vectors, A and B, and I want to calculate a scalar product, a formula which should be used when we are talking about graphical interpretation of this operation. A formula for calculating this value is here. So when I want to calculate a dot product of these two vectors, I should multiply the length of the first vector by the length of the second vector, and by cosine of the angle which is here between these two vectors. And A multiplied by a cosine of this angle, it is the length of the projection of the A vector on this B vector. We can imagine that we are going to put this vector on the B vector, and this line which is here, which is used for determining the position of the projection of this point, should be perpendicular to B vector, and the multiplication of the length of B and the projection of A, it is the result which can be calculated using this scalar product. When we are thinking about this interpretation, also we can check and we can interpret very easily the result which we obtain using scalar product for two vectors which are perpendicular. These two vectors are here. I draw here two perpendicular vectors. Perpendicular, it means that the angle between them is equal to 90 degrees. And the scalar product is calculated here. C, it is a scalar product of A and B. And C was displayed here. We see the result here. It is equal to 0. But of course, it is obvious that it is 0 because I calculated a value of the expression in which I multiplied the length of this red vector. I multiplied this length by the length of the projection of this vector on this red direction. And the length of the projection here is equal to 0. So 0 multiplied by the length of this red line, red arrow is equal to 0. Therefore, we should remember that the scalar product of two perpendicular vectors is always equal to 0. So if we want to check if two vectors are perpendicular, we can calculate scalar vector, a scalar product for them. If it is 0, it means that these vectors are perpendicular. So in practice, we use this method, this rule very, very often. Please look at this graph. We have here a vector, this blue vector, which I draw in this coordinate system. And here I have these two small red vectors. These two red vectors have very interesting coordinates. 1, 0 for this, 1, 0, and 0, 1 for this. These two vectors are called unit vectors. The length of unit vectors, of course, is equal to 1. So when we have a coordinate system, always we should have these two unit vectors. 2, if we are talking about coordinate system in two-dimensional space. Because after some minutes, we will try to generalize it and to talk about spaces in higher dimension. So we have these two unit vectors, and we have this blue vector. And for me, it is very interesting that it is possible to present this blue vector as a result of operations which we can perform on these unit vectors. So these operations are here. First, U1 vector, it is this horizontal vector, red vector. U2, it is this vertical vector. So we have these two vectors, and first I try to multiply this U1 vector by 4. So the result will be here. It will be a vector starting in this point and ending in this point. And the second vector, U2, I multiplied by 3. So the result will be here, from this point to this point. So I used twice the operation of multiplication vectors by scalar values. And after it, I added these two vectors which I obtained. So also we know how to do it because we know this operation which is related to addition of vectors. And the result is here. Using this picture, using this graph, I would like to show you that every vector which we have in this coordinate system may be generated using these two operations which we know. So multiplication by scalar value and addition, perform on unit vectors. So unit vectors are not only useful when we are thinking about the length from 0 to 1, because for me, I must say that it was sometimes a problem to assure that lengths of these two vectors, red vectors, are equal. So therefore, I use this axis method with equal parameter. But also it is very important, and maybe much more important, that every vector which we have, we can obtain using these two definitions, two operations, which I defined earlier. So multiplication by a value, scalar value, and addition of two vectors performed on unit vectors. When we are talking about vectors, very often in this context, we use this concept, vector space. So now I'm going to define this concept. Also, my goal is to talk about the interpretation of this concept, vector space. Vector space, we can think about vector space as about a container in which we can have different vectors. It is the environment in which a lot of different vectors exist. The infinite number of vectors. So we can think that this container is here, is related to this coordinate system, and here we can put a lot of different vectors. So this space, it is a space, it is a plane on which we can draw different vectors. So it is the idea of vector space. It is a container, a plane on which we can draw different vectors. But also, we should remember that when we are talking about vector space, we should define two operations which can be performed on these vectors. The first operation, it is a multiplication by a scalar, by a numerical value. The second operation, it is an operation in which we try to add two vectors, addition. And of course, we know how to perform these operations. So this space in which we can generate vectors, and in which we can perform these two operations is called a vector space. And this concept, vector space, is very, very, very useful. Very useful and very, very popular in mathematics and linear algebra. Vector space, a container in which we can have different vectors, and we know how to perform these two operations. It is a vector space. We can perform operations. We can perform operations on vectors, and we know these operations. It is multiplication by a scalar value and addition of vectors. So when we have some vectors, for example, n vectors, we can perform this operation. We can multiply every vector by a given value. These values, these coefficients, these scalar values which we use for this multiplication are here represented by these lambda values. Lambda 1, we use this value for multiplication by vector x1. Here lambda 2 is multiplied by all elements in vector x2, and so on. After multiplication, of course, we obtain some vectors which we can treat as results of these multiplications, we can add them. So it is a formula. It is a formula which describes this operation which can be performed on the set of vectors. And this operation is called a linear combination of vectors from x1 to xn. So this formula has its name, specific name, and this formula is called linear combination of this vector, of vectors. So we can take some vectors from a vector space and perform these operations. Of course, it is necessary to know values which are assigned to these lambda parameters, and the result also it is a vector. We should remember that here we have multiplication vectors by scalar values, and we obtain here vectors, and after addition operation also the result has a form of a vector. So the final result of it is a vector. It is a vector. And this operation is very common in every vector space. For many reasons, we can perform this operation. And also, in this case, because we know that after performing this operation, the result has a form of a vector. We will obtain a vector. And we see that this vector was produced as the result of this linear combination. So this result vector was produced by these vectors from x1 to xn, and therefore we can say that between this result vector, this vector which was produced, and these vectors which we have in the set from x1 to xn, between them exists a linear dependence. So the result vector is dependent from these vectors which you have here in this formula. So when we say that some vectors are dependent, linearly dependent, it means that it is possible to produce this vector using linear combination of other vectors. If it is not possible, then we can say that vectors are independent, are linear independent. It means that there is no possibility to produce one vector from this group by performing linear combination. It is not possible to present one vector from this group as a linear combination of other vectors belonging to this group. If it is not possible, then we can talk about linear independence between these vectors. And these two concepts also we will see will be very, very important. So we have some remarks, I know, very simple remarks about vectors and about vector space. Now, I think that we should say something about matrices. About matrices, which also we know very well, because we use very often matrices in mathematics, in statistics, in computer science. So I think that everybody met this structure. It is a rectangle with some rows and some columns. Here on this picture, we have n rows and m columns. This object has rectangular shape, and we have values. Values which are located on the intersection of every column and every row. And position of every element is defined by these indices, these two numbers which we have. The first can be interpreted as a row number, and the second we can interpret as a column number. So it is a matrix. It is a matrix, very, very popular concept. First, some remarks about operations which we can perform on matrices. Because the situation here is similar to the situation which we had with vectors. Also, we can perform some operations using matrices, and also it is very important for us that some of these operations, have very interesting and very simple interpretation, which may be useful from practical point of view. Addition. We can add two matrices. Here we see the example, the first matrix, the second matrix, and we should add corresponding elements. In the similar way, we can define subtraction of two matrices. In this case, we should subtract corresponding elements. What we should remember when we are talking about this operation, these operations, addition and subtracting, that the size, it means the number of rows and number of columns, should be the same for the first and for the second matrix. We should use matrices of the same size. Only in this situation we can add or subtract matrices. It is a condition which always must be fulfilled, always must be satisfied, that number of rows and number of columns in these two structures, in these two matrices is the same. And how to perform it using Python language and NumPy library. I created these matrices. These matrices A and B are the same as we see here. So you can see here in this example how to define matrices using Python language. Because Python language is very specific, and among standard data structures which we have in this language, we do not have matrices. In our language, of course, it is the main data structure. In Python, no. So if we want to define matrix, we must use this NumPy package. And the definition is here. It is the first matrix, this matrix. And it is, we can say that it is the first row, the second row, the third row of this matrix. But when we are talking about Python language, this matrix, these rows, are defined as a list of lists. And every inner list represents one row. Here, in the same way, I defined the second matrix with these values 0, 0, 7, 5, 2, 1. I wanted to add them. So notation is very simple. Plus operator is using to represent this adding operation for matrices. But of course, we should have matrices for both sides of this operation. And of course, these matrices should have the same size. And the result we can observe here. A matrix, this matrix is here, B matrix is here, and C matrix, this matrix, is here. When we use print operation, they are displayed in this form, and looking at this, we see that also that matrix is represented as a list of lists. So it is the first operation, addition. The second operation, it is a multiplication by a single value, by a scalar value. So the same situation which we have with vectors. We have a matrix, this matrix is represented by this part of this code, and I want to multiply this matrix by a value 2. So here we have this expression, 2 multiplied by A, and A, it is a matrix. The result, here we have the original matrix A, and after multiplication here, B. So we got this matrix which we have here. So also, it is very simple. The result has a matrix form. The size of this matrix is the same as the size of our original matrix. So we can go further. Next operation. Matrix multiplication. Matrix multiplication is defined here. It is a rather specific operation. It is rather specific and very interesting operation. It is an operation which is performed on two matrices. So we can multiply one matrix by another matrix. We see here this example, this matrix and this matrix. It is very interesting that number of rows and number of columns for these two matrices is not the same. So this condition is not necessary here. But we have another condition, which is very important for matrix multiplication. It is a condition which says that the number of columns in the first matrix must be equal to the number of rows in the second matrix. It is a condition which always must be fulfilled. Number of columns in the first matrix must be equal to the number of rows in the second matrix. So it is very, very important for us. So always we should remember about this condition. But there is no conditions related to the number of rows in the first matrix and the number of columns in the second matrix. We can use any values for it. But please look at this result. It is the result matrix. We will calculate values which we will have in these cells, in these fields, but please look at the size of this structure. Here it is 2 rows and 2 columns. But it doesn't mean that always the result matrix has this size, because the size of a matrix which will be produced by this operation is defined by the number of rows in the first matrix. Here, please look at this matrix. In this matrix, we had 2 rows, and therefore we have 2 rows in this matrix which is produced as an output of our operation. And number of columns is equal to the number of columns in the second matrix. Also, in the second matrix, we had 2 columns. Therefore, we have 2 columns in the result matrix. So we know how to establish the size of this matrix which will be produced as an output. It is a number of rows from the first matrix and number of columns from the second matrix. Now we can talk about the values which we will have in this result matrix. Please look at this field, at this position, which is marked here with this green circle. It is a position on which we should put a scalar product of 2 vectors. It is the first row from the first matrix and first column from the second matrix. So here it is a place in which we should put a scalar product of these 2 vectors. These vectors which are marked here using these red and blue lines, circle lines. So it is a scalar product of these 2 vectors. Therefore, I introduced this operation some minutes ago when we were talking about vectors. And therefore, it is important to have these 2 matrices in which the number of columns in the first matrix is equal to the number of rows in the second matrix. Because only in this situation it is possible to calculate a scalar product for these 2 matrices, for these 2 vectors. The length of these vectors must be the same. And it is the same because the number of columns in the first matrix is equal to the number of rows in the second matrix. So we should calculate a scalar product. So we should calculate these products: 1 multiplied by 0, 2 multiplied by 1, 4 multiplied by 5, and after it we should sum up these values, and the result is here, 22. So we should put this value 22 on this position. This position, marked by this green circle, will be calculated as a scalar dot of these two vectors. The first row from the first matrix and the second column from the second matrix. And scalar product we should put here. This position, it is the result which we can obtain using calculating scalar product of the second row and first column. And this last position, it is a scalar product of second row from the first matrix and second column from the second matrix. And the result, final result is here. So we see that we can perform much more calculations when we try to multiply two matrices. But of course, we have very simple function, very simple operation in Python, which we can use for performing it. So these two matrices, which we have in this example, I defined here. The first matrix, it is an A matrix. The second matrix, it is a B matrix. And I multiplied them. Multiplied using this meaning, this understanding of multiplication, which we discussed here. To multiply matrices, we can use the same two versions of notations which we use for scalar product. So we can use dot function, or we can use this add operator. And the results are here. So we see this result matrix here, and it is the same matrix which was obtained using these manual calculations. So it was the operation which was related to multiplication. I have a question to you. Do you want maybe some minutes break? Maybe 7 minutes. We have now 3 minutes past 6, so maybe we will meet at 6:10, okay? Okay, thank you very much. So 7 minutes we have for coffee or tea, and we will meet at 6:10. Thank you very much.
Sorry, may I have a question, please?
Yes, of course, yes.
Ah, thank you very much. Sorry, I logged in honestly accidentally because officially I didn't.
Sorry, but I can't hear you. I think that we have some problems with connection.
Choose this.
Yes, yes. I can't hear you.
Okay, I try again. My question is that will you share or send this presentation?
Yes, yes.
Oh, great.
On the chart, you have the first information from Sandy, and it is a link to this notebook. I share this notebook with you also because you see there are some pictures here, so also there is a folder with all pictures which I use in this presentation. So all materials were sent to you.
Thank you very much. Goodbye.
Thank you.
Thank you. Thank you.
Thank Okay, I think that we can continue now our meeting, and We talked about matrix multiplication. So now it is time to talk about matrix transposition. So matrix transposition, it is the next very simple operation which we can perform on matrices. Matrix transposition is very simple. To obtain transposed matrix, we should change rows and columns. For example, here, we have a matrix, and we see the first row, 1, 2, 3. And we put this matrix as the first column in the result matrix. The second row, 4, 5, 6. And we put this column here as the second column. The third row we use here as the third column. So very, very simple operation which is related to using different way of arranging elements in this matrix. We have a matrix, this matrix here, with elements 1, 2, 3, 4, 5, 6. This P matrix, and I use capital letter for representing as the name of this object. It is important because, you know, in Python, there is a difference between capital and lower letters, upper and lower letters. So this original matrix is here, and the matrix after transposition is here. In this example, I use different matrix, different from this which we have on this picture, which I found on the internet. I use different matrix in my example because I wanted to show you the way in which number of rows and number of columns will change or changed as the result of transposition operation. It is, of course, very simple. Number of rows in the original matrix is equal to the number of columns in the output matrix, in the result matrix. And number of columns in the first matrix, in the original matrix, is equal to the number of rows in the second matrix. So this operation is very simple. It is not necessary to perform any calculations. We should only change positions of elements. But we have a function, transpose function. This function is used for performing transposition operation. And next operation, it is an inverse operation. Inversion operation. So how to perform? First, we should remember that we can calculate an inverse matrix, so we can perform inversion only for matrices in which the number of rows and columns is the same. These matrices are called square matrices because they are represented by a square. This shape is similar to a square. Number of rows is equal to the number of columns. So only for these matrices we can calculate the inverse. We can perform the inversion operation. And this operation, inversion, produces a matrix. So also as the result, we will obtain a matrix. And this matrix, which we will obtain, will be equal to identity matrix. It will be an identity matrix. Of course, I know that now I should define this term, identity matrix. It is very simple matrix in which we have 0 values, except of values which we have on a main diagonal. So on position which we have in the intersection of the first row with the first column, the second row with the second column, third row with the third column, and so on. These elements which lies on the intersection of rows and columns to which the same number is assigned, the same position is assigned, these elements, they form diagonal, main diagonal of this matrix. And in the identity matrix, all these elements are equal to 1. So on the main diagonal, we have values which are equal to 1, and on other positions outside, beyond this main diagonal, we have values which are equal to 0. So it is the identity matrix. And we can remember, we should remember that this identity matrix is produced as the result of multiplication of the original matrix and the matrix which we can obtain using inversion operation. So there is the example. Here we see this example. We have a matrix here, P matrix. This matrix is here. And I calculated the inversion of this matrix. It is a square matrix, so the number of rows is equal to the number of columns. So it is possible to calculate the inversion for this matrix. I use this function inv. This function is used for calculating inversion. So compute the inverse of a matrix. So this function inv was used by me. And inv parameter is P. It is a matrix which we are going to use during this inversion operation. And the result is here. It is this R matrix. So we have P and inverse of P, which is assigned here to R object. And we remember the definition. The multiplication of original matrix and the inverse matrix is equal to identity matrix. You can check. P, it is the original matrix. I multiplied it by R. R, it is the inversion of original matrix. And the result I assign to C. This C matrix, it is the result. And I printed this matrix here. And the result is here. The result is here, and it is a matrix. The size of this matrix is the same as the size of original matrix, 3 columns, 3 rows, because it was a multiplication of 2 matrices, the first with 3 rows and 3 columns, and the second with the same number of rows and columns, and the result also has the same shape. And please look at this matrix. On the main diagonal, we have values which are equal to 1. 1, 1, 1. Outside the main diagonal, we should have values which are equal to 0. But here we see that they are not equal to 0, but they are very close to 0. Please look at these values. For example, this value. This value here at the end has E letter minus 14. So it means that this value 1.24 should be divided by a very huge number, value 1 with 14 zeros. So it is very close to 0. It is not equal 0, but it is value which we can treat as a value equal to 0. We did not get exact values. It is the approximation, because we perform some calculations using real values. And we should remember that every computer, during calculation in which we use real values, always produce some errors. So the result is not equal to the exact value which we should get. But of course, it is not a problem for us. We can treat these values as values equal to 0. So it is the identity matrix. This matrix is equal to the identity. So it is the original matrix. It is the inversion of this matrix, which was calculated using this ENV function. And here we checked that it is the inversion because the multiplication of these two values, two matrices, is equal to identity matrix. And next element, which is very important for us, it is a matrix determinant. Matrix determinant, it is a value. It is a scalar value. It is a number. It is a numerical value. It is a value which can be assigned to every matrix. And we know different methods. I think that some of you met these methods maybe in secondary school, maybe during classes or lectures at the university, which we know some methods which we can use for calculating this determinant value. For example, when we have a matrix with 2 rows and 2 columns, we should multiply these 2 yellow values and these 2 black values and to subtract these results. And it is a value of a determinant. When we use matrices with 3 rows and 3 columns, the method for calculating the determinant value manually is rather complex, because we have this matrix here. We should repeat the first and second column here, so we see that these 2 columns were copied here. We should draw this red line and this blue line. After it, we should calculate the product of values which we have on every line, and we should add all of them and all of m, and finally we should subtract this value 15 from this value. It is a rule which we use very often for manual calculation of determinant. Of course, using Python, there is no necessity to do any calculations manually, because when we have this value here, this matrix here, P matrix, with values 1, 2 in the first row and 3, 4 in the second row, we can calculate the determinant of this matrix using this det function. And it was calculated and it was printed here. Also, for bigger matrices, it is possible to calculate a determinant. For this matrix, which has 3 rows and 3 columns, also I use the same function, det function, and this determinant was calculated. It is here I had this matrix which we see on this picture. So we see that, yes, it is true that the determinant for this matrix is equal to 105. So we know how to calculate determinant value, but how to interpret it? There are many different situations in which we can interpret this determinant. I will say some words about it in, I think today, in when we will be talking about rank of a matrix and also in other situations. Because the way in which we will interpret this value is related to the situation in which we use matrices. We will talk about it. And next, very important issue which also is related to matrices, the rank of a matrix. It is in many applications, this concept, the rank of the matrix, may be very important. So I think that also we should remember about it, and we should know how to interpret this concept, this value. The definition is here. Matrix rank is defined as a maximum number of linearly independent rows or columns in the matrix. So we have a matrix, for example, in this program. I defined this matrix. This matrix is here. And the rank of this matrix was calculated here by the use of this function matrix rank. A matrix, and I calculated the matrix for this rank. And this matrix, the value of the rank for this matrix was displayed here. It is 3. So the rank of this matrix is 3. It means that we have 3 linearly independent rows and 3 linearly independent columns in this matrix. Linearly independent, it means that it is not possible to present a column of which one column from this matrix as a linear combination of other columns. And it is not possible to present any row from this matrix as a linear combination of other rows which we have in this matrix. It is not possible. Therefore, rank of this matrix is equal to 3. Also, I calculated determinant for this matrix. Why I calculated it here? Because when the rank is equal to the number of rows and to the number of columns, because we are talking about square matrix, then matrix determinant is different from 0. It is here equal to 2. So it is not equal to 0. The second situation. Program is practically the same, only I use different matrix. This matrix is here. In the first row, 1, 1, 1, in the second 1, 2, 4, and 3, 6, 12. Matrix rank calculated for this matrix. It is 2. Why it is 2? It means that in this matrix we have one row or one column which can be calculated as linear combination of other columns or other rows. Please look at this matrix. Please look at the third row. We have values 3, 6, 12. And in the second row, we have values 1, 2, 3, 4. Please multiply every element from the second row by 3. We will obtain the third row. So we can see that we can obtain the third row in this matrix by multiplication of the second row by value 3. Every element I can multiply by 3, and in this way I can get this third row. So these two rows are very strongly connected. One of them can be expressed as a second of them after multiplication by a scalar value. And therefore, the rank of this matrix is equal to 2, because we have only 2 independent rows. It is not possible to produce the second row by multiplication elements in the first row by a scalar value, or by multiplication of the values from the third row by a scalar. Therefore, the rank is 2. And determinant value is 0. So when we got 0 as a determinant value, it means that we have 2 columns or more, or 2 rows or more rows, which can be calculated by multiplying other columns or other rows by some constant values. And the last example. We have a matrix. This matrix is here. And the rank of this matrix is 1. It means that we have only one row or one column. In this case, we have one row which is independent. Other rows are dependent from this first row. Please look at the first row. 1, 2, 7. Elements which we have in the second row, we have 2, 4, 14. Elements which we have in the third row, 3, 6, 21. So the second row can be obtained by multiplying the first row by 2. The third row can be obtained by multiplying elements from the first row by 3. So they are dependent. And therefore, because we have only one independent row, the rank of this matrix is 1. And determinant is 0, because we know determinant is not equal to 0 only if the rank of a matrix is equal to the number of rows or number of columns, because we are talking about square matrix. You remember this concept which we discussed earlier, vector space. We remember vector space, it is a space, it is a container, it is an environment, it is a plane. Plane maybe not is a good word, but it is, I think that this word container is the best in this context, in which we can have different vectors, but different vectors which are from which, and all of them have the same dimension, the same number of elements. For example, if we have vectors in the space, two-dimensional space, and here we have second vector space, and the dimension of this space also is equal to 2. So please imagine that we have two vector spaces, two containers, in which we can have vectors. Vectors for which we know how to perform multiplication by a constant value and addition operation. We have these containers, and we want to know how to transform vector from the first space to the second space. We want to move one vector from one space to the second space. How to do it? If we want to perform this operation, we should define a matrix defining this operation. Because when I'm talking about vector transformation, so because I said, I want to transform a given vector to another vector. I want to transform it. I want to change it into another vector. But of course, when I want to make these changes, I must know how to do it, what changes I should do. Of course, when we are talking about vectors, we can imagine that all changes are related to some changes which we made with coordinates. Sometimes also with a number of coordinates. We can change the number of coordinates, or we can change values of coordinates. These operations we can make on vectors. These transformations. But how to describe it? How to define rules which can be performed for defining these transformations. We can think that it is very complicated, but it is very, very simple. When we are talking about transformations, vector transformations, to say exactly what I'm thinking, when we are talking about linear transformations, we should remember that this transformation is defined by a matrix, and conducting all these rules which we have defined as the definition of this transformation is very simple. We must multiply this vector by this matrix. So, for example, I have a vector A. This vector A is here. It is a vector with two elements, 1 and 2. It is a vector which exists in two-dimensional space because it has two coordinates, two elements. And I want to transform this vector. I want to transform means that I want to multiply a matrix which defines this transformation by this vector. This matrix is here. So it is a matrix with elements 1, 3, 5, 2. It is a matrix defining this transformation. And I want to use this transformation defined by this matrix to transform this A vector. So I want to multiply this T matrix by this vector. In this way, which we use for multiplication of matrices. And the result is here in B. So B, it is a vector in which we have vector A transformed by the transformation which was defined in this matrix T. And the result is here. 7, 9. It is the result which we obtained using rules defining transformation T to the vector A. So I had a vector 1, 2, and after transformation T, I have a vector B in which I have a result. So you see that this concept is very, very simple. So we can say that defining a transformation means that I must have a matrix in which this transformation is defined, performing the transformation. It means that I have a matrix with a definition of this transformation, and I should multiply this matrix by the vector which I want to transform. And the result is here. The result is here, 7, 9. But please look at this line. In this line, I calculated the inverse of T matrix. So I perform inversion operation. And I inverted this matrix T, and the result is here, C. It is the inversion of T matrix. And now I use this S matrix as the definition of the transformation. And I used this transformation for vector B. Vector B, it is the result of a transformation which was defined here in vector T. So it is, and I perform this transformation, and the result is here in vector C. And I display this vector, 1, 2. 1, 2. It is the same vector as A vector. So I had a vector A, transformed it using T matrix, and I obtain B vector, and after it I transform B vector using the S matrix, and this S matrix, it was the inverse of T matrix. And the original, the first vector with elements 1 and 2, I obtain as the result. So I think that now you see why this operation, which we discussed earlier, is called the inversion. Because this operation is useful for generating inverse matrix defining inverse transformation. So I can produce vector B from vector A using T transformation, and I can produce vector A using vector B using a matrix which is inverse matrix in the relation to the first matrix. So we see how to perform transformation and how to define and perform inverse transformation. So it is, I think, very, very interesting that for every transformation, we can find in a very simple way the inverse transformation using this inverse matrix. We have here very simple case because our transformation was from two-dimensional vector space to another two-dimensional vector space. So I did not change a number of elements. Sometimes I want to do it. And here we have a transformation in which I will transform a vector from three-dimensional space to a vector from two-dimensional space. So I'm going to transform a vector with three elements from the example this vector A with elements 1 to 3 to a vector with two elements. So I wanted to change the dimension of these vectors. How to do it? It is possible, but we should define a transformation using a matrix which is a rectangle matrix, which is not square. So the number of rows is not equal to the number of columns. And this matrix is here. It was defined here. This matrix is here. And I'm going to use this matrix to transform vector from three-dimensional space, this vector. So I wanted to define this transformation. It means I need to calculate the product of T matrix and this vector. And the result, T matrix, that is a matrix with two rows and three columns. This vector, which I want to transform, it is a vector with three elements, which will be treated as a column vector, because only then it is possible to calculate scalar product. And the result is here. Also, it is a vector with two rows and one column. It is displayed in this form here, but when we are remember about strict rules which we use for calculating the number of columns and number of rows, then we know that it is a column. So we change not only values, but also the size, the number of elements in this vector, because we use this transformation matrix. But using this matrix, we moved from three-dimensional space to two-dimensional space. And there is a problem with inverse transformation. Because in the previous example, I defined the inverse transformation as using the inversion of a transformation matrix. I use inversion operation for defining a matrix defining inverse transformation. In this case, unfortunately, it is not possible, because we can calculate inverse matrix only for square matrix, when the number of elements is the same for rows and columns. If not the same, then it is not possible to calculate it. Of course, there are some possibilities, some solutions which we can use for solving this problem. One of them is shown here. It is a transformation matrix. This matrix, which we had here, but I added one row with value 0, 0, 1. And then in this way, I produce a square matrix. And this matrix is square. And I use this matrix for calculating the result, the vector after transformation. But this vector has two elements, the same which we had before, -2 and 11. And this third element, which is not necessary for me, but it is here only for the possibility of calculating inverse matrix. And then I calculated inverse matrix, and the result is here. So 1, 2, it is an original vector. But of course, we have this extra element which is not used by us. Of course, it is a method which we can use in practical situation. But when we are talking about theoretical aspects, it is not possible to calculate the inverse matrix for matrix which is not square. The next concept which I wanted to present, it is a concept which is related to eigenvectors and eigenvalues. But I know that we should finish at 7 p.m. Polish time. So I think that we will start our next presentation on Wednesday, talking with this topic. So that's all for today. Thank you very much. As I said before, this presentation you can find on this Google Disk, and it was very nice for me to meet with you, and I hope that we will meet also on Wednesday during our next lecture, and also with some of you I will meet also on Wednesday. Thank you very much. On Wednesday during the lecture about statistical analysis of data. Thank you very much. It was a pleasure to meet with you.
Thank you for the lecture. It was really helpful.
Thank you.